best configuration of our graphics Core Next chips with Polaris 10 and Polaris 11 to really enable superior and much greater graphics efficiency than we had previously. We also wanted to make sure that we had a substantial feature set for end users that really help drive future-proof technologies ranging from monitor support, but also making sure that we're fully up to speed with the latest multimedia IP supporting the latest codecs, HEVC, and forthcoming with VP9. And we also really wanted to make sure that we delivered cool and quiet gaming, and FinFET technology really allowed us to help change the game and deliver that cool and quiet product, along with various power management techniques and architecture changes that were rolled into this product that I'll detail a little bit further. So one thing I really wanted to highlight was that this is our 4th generation of Graphics Core Next. But one of the fantastic things about our Graphics Core Next architecture is how extensible and how we've been able to continually update it over time, adding support for Mantle, Liquid VR, DirectX 11.1, 11.2, the various OpenGL releases, making asynchronous compute, which wasn't even on the roadmap when we first came out with our Graphics Core Next architecture, by updating our graphics firmware in the driver to allow for asynchronous compute all the way back to our HD 7000 series of products. So it really just sort of goes to show you how good of a purchase you make when you make a Graphics Core Next graphics card purchase. And with our 4th generation of Graphics Core Next architecture, we're really going to sort of drive that beyond and make sure that people are getting that exceptional value and getting features that are going to give their product longevity. Big eye chart there. I'm going to go into, in the slides following, a few of these in specifics that I've talked about at a very high level, and I'll jump into those in the slides forthcoming. But let's talk about the RX480 in specifics first. In the conversations I had with you previously, we never actually put this slide up. They did come up in some slides that were sent to you, but let's talk about this in a little bit more detail. The key thing with these products is delivering a balanced architecture. So, in principle, before I talk about the specifics on the side, we want to design this to be pretty balanced, and we have designed this with roughly a 4:1 texture to pixel ratio. Very nice and balanced. We've paired it up against an improved 256-bit GDDR5 memory interface. G5, whether we like it or not, it's here to stay for some time. It's used in the consoles. It's a commodity in the industry too. So let's leverage that, make sure that we're actually delivering a fantastic solution for all parties using devices that have come out. We've increased the speeds on our PHY. We've also increased our efficiency with Delta color compression, making that 256-bit GDDR5 memory interface a very good choice. Of course, this is built on the 14nm FinFET process through our Global Foundries partner, and this is our 36C compute unit product in its full configuration. What we have done substantially is we've changed the L2 cache. We've increased the size of the L2 cache, which helps us in a number of situations. And we've upgraded our display interface and our whole multimedia IP portfolio so that we are, again, industry leaders with all our display IPs and multimedia, making sure that you buy a graphics card, it's keeping up with the times so that it, again, becomes a product that you can keep in your system for a number of generations and not have to worry about, will I have to upgrade it next year? Am I missing something? Is there something that I should really wait for? So, jumping into it, the 4th gen of GCN really focuses on a philosophy of efficiency. And we've done that through a number of new features and improvements to our architecture. The first thing we did was we enhanced our geometry engines. So one thing that we did was included a primitive discard accelerator. And what this does is it really just looks at your triangles in the triangles that are in the render pipeline, and if they're overlapped and not visible, discard it. We call them. What that does is provide substantial performance improvement, especially when it comes to MSA, increasing levels of multi-sample anti-aliasing. At the highest level, 128 triangles per pixel, a lot of triangles per pixel there. We're seeing upwards of 350% performance improvement versus primitive discard off versus primitive discard on. We also have a new index cache for small instance geometry. And what this really does is it helps us reduce data movement across the chip and across the bus, and helps free up internal bandwidth for other tasks. And it helps you improve, maintain or improve throughput. The nice thing about this is that this seems fairly complex. It seems like it's something that developers are going to have to really plan for and look at using. Great thing about this is it's done behind the scenes, it's handled by the GPU, absolutely transparent to the developer. So write your code, let the GPU do what it needs to do, and you get these benefits natively. We've also substantially improved our shader efficiency. So a number of questions I was receiving from people over time as we talked about the performance for water improvement and how we're getting to this efficiency. The question was, well, how much of this is from 14 nanometer and how much of this is from the architecture? So roughly about 15% of this is from shader efficiency improvements, and that's a 15% improvement per seed. So some of this is done through instruction prefetching, which helps prevent pipeline stalls, so that way the GPU is actually doing what it needs to be doing, rendering graphics, displaying your graphics on your screen, and not waiting for things to come through the pipeline. We've also tuned our L2 cache. One thing that's always costly is when you're moving off chip into memory. Those transfers are costly. For example, when you overflow graphics memory, you always know when you're going to non-local memory, that's the long way around, and we always want to avoid that. So doing this, on top of the increased cache size, really helps improve our efficiency across the board. And then we have native FP16 and Int16 support. Decreasing the register footprint size is always a benefit, and it also helps with improving our power efficiency as well. This is beneficial in a number of different situations. Computer vision, data learning, big buzzword that's always floated around is deep learning. But again, it's a huge benefit to graphics as well. So 15% of our performance improvement over similarly performing products like the RX480 and RX290 is what you'll be seeing. Sorry, the R9290. We also have GPU open shader intrinsic functions. Rich is going to talk a little bit more about GPU open later on when we dump into the software side of things. But GPU open is actually helping us enable, with these shader functions, easier console to PC and vice versa, PC to console porting and developing. So what we're giving is direct access to the ISA, and as well as direct access to the ISA. And we're also enabling performance critical functions that allow a developer to code it for a console and it'll execute exactly as they planned on the GPU, which is very, very important. This has been made available on DirectX 11. I believe DirectX 11 that was enabled end of May. DirectX 12 was around May 24th, and Vulkan as well. So all the latest APIs are now enabled with these shader intrinsic functions, allowing developers to make themselves much more effective developing their games. We've also improved our memory subsystem and delta color compression engines. So lossless delta color compression is something that I first got a chance to speak to a number of you about back on the R9 product. And essentially what this allows you to do is compress textures and objects efficiently and allowing you to provide the performance that you would previously on a very wide bus, but do it efficiently on compressible textures on a more reasonable bus, a 256-bit bus, a 128-bit bus, making sure that you put your silicon efforts and your cost into the GPU and not have to be adding multiple devices. So a great example is the R9 again. This is a product that we launched at the end of 2013. And then we have something like the RX480. So on compressible textures, you're getting roughly a memory bandwidth, peak bandwidth gain with delta color compression of about 40% over that product. Again, when you have an efficient balance of resources, it yields you a higher peak bandwidth. But in addition to this, what's also a nice upgrade to this as well is completely update our memory controller in 5. So what you're going to see is this supporting up to 8 gigabit per second on the products. The products that you reviewed are now supporting that. So again, we're keeping pace with the GDDR5 memories, making sure that we're pairing, making the sensible decisions across the board for our product configurations. I mentioned on the architecture slide, we've doubled our L2 cache size. Again, moving information off the chip into local graphics memory is a costly thing because data transfers are always costly. We have done this and increased our power savings on these transactions through the tweaking of our caches as well as leveraging into the benefits of DCC. And this has netted us over a product like the R9 roughly about a 40% savings on memory transactions overall from the power perspective. That is fantastic, really highlights what we're trying to do, deliver great performance at a very efficient power envelope. Is this your water or my water?
It is. Mine.
So, asynchronous compute. I love talking about this, and Richard is going to talk to you about this in great detail in the software perspective because this is a game changer. So, asynchronous compute is fantastic, and we've made it available all the way back to our 7000 series of product through software updates. It's particularly critical when you start looking at VR and other things where timing is essential. So there's a few different flavors of asynchronous compute. Some are better than others. You have the typical asynchronous compute where you're running your graphics workload. It has the priority. Game developer requests a compute workload. It will still give the priority for completion to the graphics workload, but it will run the compute workload at the same time, filling up the GPU to 100%. Graphics workload finishes, it has priority, compute workload will finish when it can, based on availability of resources, really still gives the priority to the graphics. It's great, but if timing for this compute workload is essential, you can run into some challenges. Well, then there's this next one here, compute preemption of graphics, where, okay, great, I'm running our graphics workload, but I have a really, really important compute workload that needs to be run. So, okay, finish the graphics workload, run the compute, finish your compute workload, and then run your graphics. Great, you've given the priority where you need it to be, especially if compute's pretty important. But you gotta watch out for these valleys here. Well, what do we always want to do? We always want to be making sure we're making efficient use of our GPU and utilizing it 100% so you're getting the ultimate performance. These valleys here are not good because those are instances in time where the GPU is kind of going, what do I do now? I'm waiting for my graphics workload to finish, then I need to start my compute, and vice versa. You're not keeping it busy, and that's not good. So, This is really derived off of our work with VR. Quick response queue. You get the benefits of both worlds. You get your graphics workload running as it should, and you can slice off a minimum amount of graphics workload that you want to allocate to the GPU at each time. But, for example, in VR, where timing is essential, being under 11 milliseconds to do various transformations, you want to make sure that compute can run when it needs to be and finish in the proper amount of time. Quick response queue allows those graphic workloads to continue, but gives priority to the compute workload as the developer intends, and allows that compute workload to run in a very critical and essential time frame. Make sure that you stay within that 11 millisecond time frame for VR, and then continue with your graphics workload afterwards. This is what really makes Graphics Core Next and AMD's Radeon products stand out from the rest of the world. And how are we doing that? Well, we actually silently put this back in our firmware and other products, but we actually have hardware schedulers that really, really benefit us when it comes to asynchronous compute. It's built into our GPUs and helps us schedule these compute shaders when required to do the warping and display presentation, particularly for VR headsets. More and more games are having compute content. Our asynchronous compute engines and our hardware scheduling is really going to allow us to give developers access to the shaders in a very efficient manner and basically provide access to the compute unit in a very unobstructed way so that we can actually get the work done when we need to be done in those very time-critical environments. So, in summary, before we take a little bit of a break, probably running a few moments early, but that's okay. We have revamped the architecture in a very substantial way. We've done it through our FinFET technology choices. We've tuned the architecture specifically for gaming. We've made particular physical design optimizations, and for everyone I'm assuming everyone has posted a review, we've really optimized how we've done our DPM on these products to make sure that we're running on the very efficient part of what I like to call the voltage frequency curve and the clock performance curve. So that way you're riding that curve, but you're not on that part where it's flat, where you keep on adding power and clock, and it ends up being a return of minimal gains. So we've enabled up to 15% performance improvement per compute unit versus comparable products in terms of performance and the first generation of the use of that ASIC versus the 480 and the R9 and versus other products that sat in this sort of price category 2 to 3 years ago, something like the R9 270X. We're providing up to 2.8x performance per watt improvements, making that that upgrade very attractive for an end user that has an older OEM system or doesn't want to upgrade their power supply. Doing it with a single 6-pin power connector and giving them substantial performance improvements without increasing the overall power budget of their system. So, 2 minutes early, but this is where we're going to take a little bit of break. Let everyone to take a little nature break. And how much time do we have for a break? Yeah. On top of what you would see from just going to FinFET. So I talked about we had performance per watt improvements from FinFET. We also have a lot of things from design decisions and optimizations on the architecture. So just to illustrate this a little bit more visually, because AVFS, showing like sensors on a part is one thing, but I'm a picture person. So if you imagine this is your voltage frequency curve with voltage on the bottom on the x-axis, frequency on the top axis. The end goal is always to be as close as possible to this optimal true Fmax capability. But because of variation, because of unknowns, temperature drift, inversions, aging of the part, AC-DC voltage margins, we have to have guard band, which it ends up keeping us in the past further away from this optimal point, having to run potentially higher voltages for the same clock, which isn't necessarily as efficient as possible. AVFS starts pushing that voltage to the left, lowering the voltage for the particular clock you need to run. So that's why we're running in excess of 1200 megahertz at voltages that you wouldn't see previously on prior products from AMD. And what that does is it really, really highlights how we're getting to this performance per watt improvement on top of FinFET.
So that curve on the previous slide is basically the curve we are seeing in the Wattman, right?
Yes. So I'm not sure if you had a chance to look at multiple cards there, but if you unlock the voltage curve, the voltage on there, you'll see from product to product, you'll see different voltages for the clocks.
So each card is calibrated by the control unit inside.
Yes.
Okay.
Yes. So it's very precise, and that's why what you'll see is let me know your experience, but when you're adjusting the clocks, were you able to adjust the clocks very high from its default setting before having to change voltages, or what was your experience?
Personally, I didn't change voltages because I didn't have enough time for the review. But I don't see is there any benefit by using the manual curve adjustment? Considering that it's already optimal curve selected by the control unit.
It was by design to force you to use the slider up front, because slightly educational. We want people to know that these curves weren't chosen at random. But also you'll probably see that you might get as you start changing the clocks independently. Might be very, very small changes you can make on top of adjusting the curve by percentages. So it's a little bit educational. Play around with it. If you have questions, work through Ian and your local PRF, come to me, and I'm more than happy to sort of share my experiences afterwards. So we are getting up to 1.7x performance per watt from FinFET. We always expect to get performance improvements from the processes, but this product is much more than just a process node change. We do have a number of technologies like AVFS, like our primitive discards, that will actually get you up to 2.8x performance per watt improvement over previous products like the R9 270X compared to something like a 470 that you'll see more in the future. Again, very efficient, and it's FinFET optimized by AMD. It's not just a process. So, in summary, this is our best graphics core yet. Come to expect that from us. We're not going to give you something subpar there. We're always improving on it, but Graphics Core Next has proven to be very, very versatile over the years. We are providing future-proof display support for 10-bit and 12-bit HDR monitors. We're giving you the multimedia support that you need so you can do high-quality CPU burden-free video streaming and decoding. And with the help of FinFET optimized by AMD, we're giving you that cool and quiet gameplay to deliver that greater than 1080p, 1440p, high refresh rate AAA gaming with a product like the RX480. So I hope this was helpful for you.
Which one executes most quickly overall? The one that, well, these all start at the same point in time, if you like. They all start by kicking off a graphics task. The GPU is completely idle because it comes up from zero usage to some fairly high utilization. And then at this point, in the various three ways of running asynchronous compute, the compute shader is submitted, and it's the same task in each case. So the graphics task here is interrupted by compute, so this is a preemption, and the compute task then executes to completion. The valley here is wasted time from the GPU's perspective. It's time where it's not doing anything. we talk about a graphics pipeline, and that's a really important point. The pipeline is always full if things are working well. And it's a deep pipe, it's literally thousands of clocks deep. So every clock cycle, each part of that pipe should be doing productive work. That's how we make a GPU highly efficient. Lots and lots of width to the pipe as well, and tremendous depth to the pipe, everything working in parallel, things are awesome. When you start the GPU up, when you give it a task, there is a significant period of time when you're not using it very efficiently. This is the upwards curve of a graphics task starting. And the graphics task trundles along, it's doing its work. The GPU, for all practical purposes, is flat out. If you do benchmarking, we'll talk about the horror of VR benchmarking, because that's going to ruin your lives as well. If you do benchmarking, you will often try to saturate your GPU. You'll make it 100% busy. And if you create this situation here, with preemption being the model for doing your compute, it will look like the GPU is 100% busy. You give it a graphics task, you give it a compute task partway through, it stops the graphic, picks up the compute, does it until it's finished, resumes the graphics task, finishes. Takes a breath and says, what's the next thing I can do? It's 100% busy as far as you as a programmer or a tester, a journalist are concerned. There is a different way of running stuff. And if you run the asynchronous shader, which is genuinely asynchronous, which is what we've been able to do in our GCN architecture for several generations, you actually can do things so that a low priority compute task runs using only idle cycles from the GPU. Why do you get idle cycles in a GPU? I often refer to this as bubbles in the pipeline. It happens, so a pipeline is ideally full of work at every stage. But it doesn't work out that way. Sometimes you say, I must just get a texture that is filtered to high quality, and it's going to take me, I need 3 or 4 textures for this particular pixel. Just go and get that for me, please. And when you've got the answer, come back, and then I'll be able to add it to the other value that I'm doing here, or do some lighting attenuation to it, and away we go. But there's quite a lot of memory transactions that need to take place. So what the GPU does is it says, okay, well, I'll do that, but it's going to take a little while, and it has a look for other compute work to do while the texture fetches are taking place, yeah? And if it hasn't got any, that's a bubble in the pipeline. That's unused compute resource on those clock cycles, waiting for the texture answer to come back. Make sense? Those are what bubbles are in the pipeline. One part of the hardware, the compute unit, or the texture unit, the memory fetch or the ALU, whichever way you describe these things, one part has been holding up the other part, and the other part can't find anything useful to do. Well, what's really cool about graphics tasks is that you often find situations where you're compute free and your graphics and your texture memory heavy. So maybe you're drawing the sky. You go and get a number out of the texture, you throw it up onto the sky. You go and get a number out of the texture, you throw it up onto the sky. Really trivial from a compute perspective, and as Evan pointed out, we have about 4 times as much compute capability as you have texture capability. That's in the diagrams, and in fact everyone builds their GPUs in this kind of way. What's happening there is that the compute units are essentially useless or unused. They're not doing anything. Just saying, wish I could have something to do. Well, if you build GCN architecture, which is what we do, then you can say, you know what, if you've got a few idle cycles on the compute side, hey, why don't you do this compute task? And the compute task might be, go and figure out whether this particular thing is going to be visible, because I think it might, and I'll draw it if it is. But if it isn't visible, then I could just kill the draw call later on. Or it might be, hey, I've got some AI. I'm trying to figure out whether the AI can see you over these hills and so on. And it's mostly mathematics that it's got to do rather than memory fetches. So it'll fit in rather nicely. And you get the situation, I talked about the GPU being 100% busy in this kind of case. Yeah, it looks like it's 100% busy because it worked flat out, it gave you the answer as soon as it could, couldn't do it any faster. But you get a situation where you can actually fit these into the little pockets of free work that just wasn't being used. And now the compute task doesn't take any clock cycles. All the way along here, it's not stealing anything from the graphics task, and it's only this little bit at the end which happens to overlap past the graphics task, where there's added cost for the compute task. You can get a situation where you can give a graphics task, you can load up the GPU, have it 100% busy, and then you can give it a compute task, and your GPU is now 120% busy, 140% busy. And that's the kind of number that doesn't make any sense. Yeah, it doesn't make any sense to say my GPU is 140% busy, but I can give you cases where we've been able to write synthetic benchmarks where you do that. Yeah, the GPU is genuinely 40% more busy than it was when it was 100% busy. These bubbles in the pipeline being filled. Really important point. Okay, so the asynchronous shaders that we've been so proud of, we run them in parallel with the graphics task, and at low priority in this case, because that's what the programmer asked for. The programmer can say, hey, give it a high priority if he wants, but you can ask at low priority. And then we just complete tasks in the order in which they're submitted while respecting the priorities, so everything's good. Here the programmer has said, hey, I want a quarter of the GPU dedicated to graphics no matter what. The high priority compute task comes in and happens to use the other 3/4 of the GPU. Notice that there's no deep valley here. Yeah, this deep valley, which is wasted clock cycles, there is no